Hi, and welcome to lesson 2. This lesson is going to talk everything about graph fundamentals. Let's dive right into graph fundamentals. So let's talk about graph fundamentals. This lesson is going to talk everything that you need to know about graphs. There's no prerequisite knowledge required about graphs to be there. I'm going to teach you all in this so that once we advance into the advanced graph use cases, everything should be a breeze for you. Graphs are versatile data structures for modeling relationships. They have applications in networks, social media, navigation, and much more. Every place wherein there's like a node and there's some relationship associated with different nodes in between them, graph is used in that case. Also, graphs can have closed loops. Graph is generally represented as G equal to V comma E, where V is the set of vertices and E is the set of edges. Edges represent the connection between nodes, and vertices are the nodes of the graph. Vertex or a node is a fundamental unit in graph. You can think of it as people in a social network. Each person represents a node in a social network graph. Edge is like a connection. It connects two vertices or two nodes and represents the relationship between them. For example, friendships between people, who knows whom. All of that is a part of creating edges or connections. Degree is the number of edges that is connected to a vertex. In degree is the incoming edges. Out degree are the outgoing edges. These two terms are frequently used for directed graphs, wherein relationship is only in one direction, the node which is getting a lot of connections. You can calculate the in degree for it and also the out degree for nodes. Let's look at the types of graphs. The first is undirected graph. Edges have no direction. For example, friendships in social network. Directed graphs, also known as digraphs, wherein edges have a direction. So there's a defined source and a defined destination, and the relationship is from source to destination, not from destination to source. The arrow in a directed graph represents the direction of the relationship in a graph. For example, following on social media. Person A is following person B, but that does not mean that person B is also following A. For cases like this, a directed graph becomes the ideal representation. Weighted graphs. Edges have weights or costs associated with them. Think of it as the distance in a road network. If you have to go from point A to point B, you can take the bus. Now, the bus would require some money for you to travel from point A to point B. That becomes like the weight for that distance between A and B. Similarly, it is also if you have to consider a water network, there's a capacity of the pipe of how much water it can hold. That becomes the weight of the pipe. So weighted graphs help us identify any kind of restrictions that we have in the edges. There are also a few special graphs. The first one is cyclic graph. They contain at least one cycle. So it would go roundabout and lead to the same node. That is called a cyclic graph. Acyclic graphs have no cycles. Example, directed acyclic graphs or DAGs. So there's no cycle. Everything might be connected, but it does not lead back to the same place. Connected graphs. A path exists between any two vertices. So you can reach each vertex to the other vertex in this graph. Disjoint graphs contains multiple disconnected components. Now let's look at a few graph representation methods. The first is an adjacency matrix, a 2D array where A of ij equal to 1 if there is an edge from vertex I to vertex j. So a matrix representation showing where there is an edge from one vertex to the other. A key advantage of using adjacency metrics for graph representation is that it is easy to implement and query. It is a simple matrix, so you can find out the position of each element. You can just query it as A of ij and do operations on it. Disadvantage is that it is space intensive for sparse graphs. If there are very less edges, you'll still create a I cross j matrix representing the number of nodes that are there, but most of it will be filled with zeros, and that is just wastage of memory. In order to see how does it actually look like, consider this graph. It is a cyclic graph 1, 2, 3, 4. So 1, 2, 3, 4, and these are the edges that you see 1 to 2, 2 to 4, 3 to 4, and 1 to 3. In case of a matrix, so I would write I need to have all of my nodes that are there. So I write 1, 2, 3, 4, 1, 2, 3, and 4. Now let's check if there's an edge between 1 and 1. There's no self loop. So I write 0. Then I check the next entry between 1 and 2. Is there an edge between 1 and 2? I come back to my graph and fill up the table as 1. Then I have to see if there's an edge between 1 and 3. I see there's an edge, so I write 1. Then I see if between 1 and 4. Between 1 and 4, no, there's no edge, so I write 0. That way, I have filled the first row of my matrix. Let's go to the second, just for more clarity. Between 2 and 1, let's see. If you see, this is an undirected graph. There are no arrows, which means that this edge is both between 1 and 2 and 2 to 1. There's no direction. So even when it is 2 to 1, you'll write a 1 here because there's an edge between 2 and 1 as well. If you talk about 2 and 2, there's no self loop. So you'll write 0. Between 2 and 3, there's no edge. So 2 and 3 becomes 0 again. Between 2 and 4, yes, there's an edge. So you'll write 1. And similarly, you'll fill it for vertex 3 and vertex 4. Interesting point, if you observe, if it is an undirected graph, along the diagonal, you'll see there is a mirror image of all the values. So you can also just fill the upper quadrant and duplicate those values by mirroring them in the lower quadrant as well. And you'll get the same result. The next graph representation method is an adjacency list, a list where each vertex is an array of connected vertices. It is advantageous because it is very, very efficient for sparse graphs. The disadvantage is that it is queried to specifics. It is slower to query specific connections, and that is a slight disadvantage. So while choosing the representation, your use case and the kind of graph you're working with also matters. Let's look at how does an adjacency list look like. Let's take the same graph, 1, 2, 3, and 4. So from 1, you have edges to 2 and 3. So you write them as a list as 2 and 3. From 2, I can go to 1 and to 4. So I'll write it as 1 and 4. In case of 3, I have a connection to 1 and to 4. So I write it as 1, 4. For 4, I have a connection to 2 and 3. So I write that connection. So this becomes my adjacency list representation for the given graph. Let's look at a few applications of graphs. The first one is network analysis. Right from social media connections to internet routing, graphs have a use case everywhere. Path-finding algorithms. Shortest path in maps, navigation systems all use graphs. Right now, everybody uses maps or navigation systems in their car when traveling from one place to the other. Even if you're new to a place, you rely on map technology and navigation to help you reach to your destination in the shortest and fastest amount of time. All of this has been possible through pathfinding algorithms running on the back end. The third application is dependency graphs. For example, task scheduling, like project management tools, all of that is done through dependency graphs. And also biological networks, gene or protein interaction mapping can be represented using graphs, and you can apply graph techniques and algorithms to make it more efficient. Now, as we come towards the end of our lesson on graph fundamentals, let's look at a few key takeaways. The first one is graphs model relationships and are versatile in computer science. Understanding graph types and representation method is essential for solving real-world problems. I hope you were able to grasp all about graph fundamentals. Take the quiz and test out your knowledge, and I'll meet you in the next lesson.